So this talk has nothing to do with aliens or silver probes. It's a discussion of a little library we put together to manage some problems we had in building distributed systems to try to make our life easier. And I think it's a tool that might be useful to others, and we certainly will invite anyone who wants to come contribute and extend the tool to join us in our quest to make more sense of what's going on in complex distributed systems. So the talk's going to go in 4 little stages. A quick teaser is what am I going to be talking about today? Probably about 5 minutes on the system context that we're coming from. So what are the problems that we're particularly trying to solve, and why did we end up in this particular place in solving it? And then it's the specific motivation for the library, and then a deep dive into or through its features. So one of the things I've observed over the years is as we write a program, there's the things that the programs are designed to do, the function that it is performing. And then there is a whole set of secondary operations, and often represented as side effects. And these might be logs, writes to a database, metrics, things that are side effects of the program's operation, but are often not considered as the primary design goal of writing the code. And so we've developed as a community a set of habits. We'll put in log statements so we can tell what was going on in our program while it was performing its primary function. And it's easy to get caught up in the primary function and to sort of forget about all these secondary and tertiary things that we need to do when we build real systems that run in the real world. And so the idea of probe is really to disintermediate a lot of the heterogeneous ways in which we expose the dynamic state of our programs to other systems, whether that's storage, or internal state that it then comes back and uses later. And so we want to create a single point of interface where all the stuff that's happening while we're computing our primary function goes into this channel, and then I can late bind and choose what I'm going to do with that state, whether I want to enable or disable logging of that state, transformations over that state, et cetera. This talk bears some similarity to a talk, and I'm forgetting the author, about ALIF, which I believe last year had very similar aims and perhaps a slightly more complex machinery. So we're working on a healthcare platform, runs on Amazon, uses a variety of distributed storage systems, and itself runs on the Immutant JBoss platform and consists of a whole bunch of application nodes sitting on top of a whole bunch of database nodes. And this project's called Switchboard. It powers a set of mobile applications and a desktop application. And it has the typical structure of any one of these applications. And what's wonderful about the world we live in today is there are many services that you can pick up and run, whether they're high-end, expensive things like Splunk. You can install Logstash. There's lots of systems we can build around this core infrastructure that looks a lot like many of the systems we may be building. But we're faced with a slightly harder challenge in that there's a lot of regulatory restriction on what we can do with third-party systems, what we can expose to them. And our customers are often hospitals, and the IS departments in hospitals are extraordinarily conservative, and for very good reason, because wrong data means people die. And so you have to be extremely careful and rigorous about how you manage not just security and liability, but the integrity of the data and the integrity and function of your systems. So as a consequence, we're striving to keep our system as simple as possible so we can reason about all these properties for which we are beholden. The system itself is designed as a loosely coupled system of modules, so relatively self-contained pieces of functionality, and they're designed to be durable. That means that at any time a node may go down, the function that it was performing may be prematurely terminated, and the system has to be set up so that function eventually gets completed. And one of the ways you make your life easier is you have it in at least once semantics. It will eventually get completed, but it might get completed twice. We want to minimize the infrastructure components. We're still a very small operation. So the operational complexity of bringing in a lot of these other systems that I mentioned, even if it's simply via an API, becomes a lot to manage for a team of 3 or 4 people getting involved in a project this complicated. So we only use 2 data stores for all of our operations. We use Datomic for all of our complex data modeling, and Cassandra for time series and for all of our bulk storage. And we prefer processes that are easily managed, single process, single node, easy to manage, shared nothing kinds of architectures. And I've had previous experience with HBase, and Cassandra has been quite pleasant in contrast. So the unit of system composition are one of these modules. It might be an API call, a queue handler that fires, And then there is often reading state from the database on that particular node. And you do a series of functional transformations, which end up in either another message, a side effect to a database, or a network I/O. Network I/Os, of course, are a special case. Now, these are relatively easy to reason about. What gets difficult is when you're dealing with an asynchronous chain of events, we'll call that an operation, which is some logical end-to-end side effect that, say, a user is expecting to see or a downstream system is expecting to see. And that has to complete reliably, and it doesn't always do it. And so it turns out it's a lot harder to reason about the behavior of an operation than it is to reason about the behavior of an action. To give you a sense of some of these actions in our system, this was an early sketch that we put together with help from actually some of the folks at Cognitect. And just thinking about the different modules that we needed to perform. We need to ingest and validate some data. We might want to perform an administrative operation, which is fairly straightforward. But we do a lot of dynamic workflows where we're taking an operation that you might often write as a single coherent block of code and breaking it up in time. It might run over months or years. And it's constantly handling state changes that take place in human time. So 5 weeks from now, do X. And then if the user does Y, go do Z. And so those decisions need to be durable and managed on the platform as systems come up and down. And it's all connected via a queuing layer. So when we're debugging things that go wrong, it's fairly easy. Given an input and the database timestamp, thanks to Datomic, we're able to get essentially referential transparency at the module level or the action level, which is we could take an input database state and we get the same result every time. So it's really easy to reason about local errors and maybe a hole in our testing. But these are also fairly easy to test, so they tend not to error very often. The errors take place when an assumption in one operation doesn't quite line up with an assumption of a downstream operation, or that the coordination among operations is something we didn't reason about correctly up front. Now, this may be a failure of imagination, but it's also a practical reality of building systems like this. So the first problem we're trying to solve is that our operation level function is impure. We don't really get pure functions. Oftentimes because these steps between operations are dealing with foreign systems where I don't get a nice idempotence guarantee. I have to be careful to debounce and never send two network requests. The data that I read is not always going to be the same. So it's, unless I'm saving everything at that boundary and working with it carefully, which can be a pain, you end up dealing with having to figure out what's going on with your operations, and oftentimes at runtime. The user says, well, I clicked on the button and nothing happens. And they're on the other side of the country on a mobile phone with a particular OS version you haven't tested yet. Now, how do we dig in and figure all of that out? We also find that we want instrumentation of what's going on in our system. So whether this is monitoring or making sense of the internal performance of the system, understanding where the latency bottlenecks are, these are one of these secondary functions. So the code has its function, it also has its performance footprint and the way that it interferes by the use of shared resources with other things that you're trying to get done. So if you're having a latency bottleneck in your system, you want to be able to reason about the relationship of all the parts. So we want to store state to characterize that particular part of our system. We need to audit anybody who looks at a piece of data we pull off of an electronic medical record. We need to know who that person was, how they were authorized, and have a complete report of everybody who ever saw that piece of data. Not so hard in the era where storage is free, but we have to reason very carefully about our system so that we understand when somebody comes in on an API request that we have an authorization associated with that request, and that all gets logged. And again, that happens outside of the main operation of looking up a time series. We often are starting to work on building models. So if we're presenting something to the user, there's their data, but how does their data compare to the population? So we're constantly updating online population models. And some of this can be done in batch mode and done offline, but oftentimes the offline batch mode is more of an administrative complexity than simply having one of these workflows that I described, FHIR, update the model dynamically as data changes. So when we started looking at the issue of reasoning about our system, in the context of all these other constraints, the idea of writing logs is kind of abhorrent to me. Now logs don't get me wrong. Logs are powerful. They're easy to generate. They're mostly human readable. Everybody generates them. All of our other systems generate logs. And there's all this infrastructure for taking these text strings, mushing them together, searching them, sorting them, visualizing them, building graphs from them. And there's a big ecosystem of supporting systems that we really don't feel we can use adequately for all the reasons I mentioned earlier. And so it's been bugging me for years that logs feel like premature serialization. Why am I going into this textual format that I now have to go through work to make sure I generate correctly, parse correctly later? Now, a lot of people use JSON as their serialization format, which means you can do structured analysis over the data, but you're also throwing away the context of the system that the data was collected in. So if I have a reference to a model object and I'm trying to reason about the behavior of my system, I don't want to dereference a UUID in my head or have to track which UUID is going through the system. I'd like to actually be able to track the model. So I want to be able to take the state that I'm storing to reason about my system and use all the state that's in the system to be able to work with it. So maybe we can keep all of the data in our system and solve all these problems at once. So the idea of probe is a simple interface to capture runtime state. We want to minimize the performance impact on the current thread so that all this other stuff can happen on a parallel thread or a parallel CPU. We want to encourage late binding decisions wherever we can. So you decide what the semantic needs of your system are, capture that state, and then have some flexibility. We might want to later say, gosh, I really wish I had instrumented that particular method, say it was doing authorization. So we have some ways where you can go in and instrument functions at runtime to capture that state, stick it into the probe chain, and then manipulate it the way that we manipulate everything else. And I'll give you some good details on this in a second. So we also want to know whether to capture. So we want to be able to turn on full tracing, look at the entire system, and then shut it back down. Maybe we want to do that just on a per user basis. So we want to get all of this, all the stuff that's going on, but we're just trying to figure out one user's problem. So rather than dragging my whole system down, I want to put in a filter that says, hey, just log for this user. Now, that's a nice thing to do that log systems don't make really easy unless you build infrastructure around it. We want to do transformations over the data. I can generate an ungodly amount of data at every point in my program's execution. I don't necessarily want to store or see all of that data. So actually filtering down the stream of all of the dynamic program state is a critical function. And then eventually we are going to have to serialize and store this if we're dealing with lots of data. But sometimes I just want to keep a rolling buffer in memory and then say stop and say, okay, what were the last 100 transactions that this user took place on my system? So I can go in the REPL, watch what's going on, connect it back to the database state, reason about the bug, and then go back to my evaluation systems, try to reproduce the error. And so these are the kinds of interactions on a complex distributed system that we want to start to enable, as we do. But we want to keep it friendly for the habits we've all built around the way that we write our logging statements and keep it as simple as possible. So probe is a simple namespace, and you call probe with a tag set and then a set of key values. So that's pretty simple. It's very much like logging JSON, which I see as a nice closure convention where you log key values and that gets serialized as a readable EDN string or a JSON string. The tag list is how we decide what we're actually going to look at runtime. So the tags are how we do the matching as opposed to a log level. And what we do is we roll the namespace and the log level into the tag set. So now you can use both the context in which the data was captured, the namespace, or you can use any user-defined additional tags that you might want to parse your data out more finely. So when this probe function runs, and I'm going to give you a little bit more grody details about exactly what could be captured at a probe point later. In this case, this is a simplified view of I capture the tag set and the key value sets. So these probe states now are being generated, and we've got to do something with them. Well, the first thing we're going to figure out is where do we want these things to end up eventually. So this is an example of a memory sink. So we create an atom, we create a memory sink, and you can actually create a memory sink that's finite. So it's a rolling buffer. And you just say add sink. So we now have named sinks, and then some function, which is going to take a sequence of maps in and then do something with them. Let's see. OK, that's coming later. So this is an example of a memory sink. These are relatively simple functions. So all this is doing is resolving the atom, and then in the function call, essentially updates that atom in place. So a memory sink, this is the sink that we use actually for almost all of our system data that goes into Cassandra. So we keep essentially an infinite log of things that we care about on Cassandra for auditing purposes and many of the other purposes that I mentioned, including the ability to trace the entire system. And so it's just essentially we have a schema, we unpack the things that we tend to want to search on, and then everything else gets dumped into a blob and stored in Cassandra. So the last piece of probe, we have a probe point, and we have a sink where it might go, and then we got to get it from point A to point B. So subscriptions are essentially a conjunction of tags that map any probe point that matches that conjunction of tags will generate a probe state and send it off to that particular sink. And this is an area where I'm not entirely pleased with the API. So this is something for which I'd be more than happy to get critique and suggestions for a better way in which we might structure the interface to the functionality. And the subscriptions can be added and removed at runtime. So the subscription mechanism is based on core async, which gives us a lot of nice properties, and one of which is we can use its composition operators to perform transformations within a subscription. So if you think of a subscription as a pipe, that pipe can do a series of filters and transformations on data and then dump that into a sink. And we had thought about doing a more complex topology. We thought we'd start with this, see how far we got, and then consider whether or not we wanted to do some sharing. There's one problem with this current structure is that if you've got two tag conjunctions that generate the same state and they end up going to the same sink, you end up with duplicate data. And so then there's some questions about do we do time-bound deduplication, et cetera. Mostly we just are careful about how we design our tag sets. So the probe data flow is pretty simple. My program's running away. I hit a probe point in the lexical structure of my code. So at runtime, that generates a sequence of these probe states. Those go through whatever functional transformations I've set up and get written into a database for forensic use later or for audit inquiries later. So the probe is actually a macro because it allows us to get at the form and to get some extra information about the lexical context of that probe point, much like most logging systems do. So we have essentially the notion of the line number here, and then the interior of the probe function can grab the dynamic bindings that are present at that point in time. So I can actually turn on a global, grab all these dynamic variables at every probe point. That gets thrown into the state map, and then for the stuff I don't care about, I filter it back out. But this allows me to look at any dynamic context that I may be passing around my system. And while I'm sure if Stuart is in the audience, he'll come and hit me on the head later. We do use dynamic context around a lot of our methods to capture the essential, what are the databases that are active, what's the authorization context of this operation, because I did build a system where everything was explicit and I got tired of all the extra typing. So it was a pragmatic trade-off, but I don't claim that it's superior to other approaches. So the full lexical context gives you a map that actually looks like this. We've got a set of tags, the timestamp at which it was captured, the thread ID in which it was captured, so you can see what was happening on the same thread, what hopped against, among threads, the namespace it was captured in, and so on. So this is what I just mentioned, the dynamic context. So you essentially say capture bindings, you give it a list of vars, and it'll look up the values of those vars and slip them into a map for you in that state variable. So this is an example of what we capture in our runtime systems today. It's quite a bit of state, but it's quite useful. So we now have the node, the lexical context, the runtime context. We've got the master database, which is the sort of master for our whole system. And then with a multi-tenant system, so every system has its own atomic database. So they're completely isolated. So I have the timestamp of my database, the application ID, so I know which database that's associated with. So I now have essentially the entire state of my system at that point in time is now available in my log. And the one exception is Cassandra, and there we don't do a lot of complex stuff. So we can either design a table to be idempotent or to not have duplicates, or we can store explicitly the time data that we need to do reconstruction. And that keeps our system relatively simple. The other thing that we have, as I mentioned, from the dynamic context, we pull out the authorization and then a tracer we call cause ID. Whenever a new API request comes in, we instantiate a cause ID, and then that is passed through this sequence, this operational state. So now I've got a tag where I can go back into my logs and say, hey, give me my program trace for this API call. So then I know that this user at this time did a call. Here were all the things that happened in the system and all the side effects, and I can reconstruct that programmatically on the live system. So we have a forensics library that we're working on. I think at some point we'll abstract this and roll it into the probe library. But essentially, it is just starting to build some abstractions around filtering over common things, extracting out subsets, and starting to build up some representational apparatus for thinking about traces as first-class entities. And I think that we're not perhaps as far down the road on that as we'd like to be, but I would love to have discussions with people who are interested in this about how do we think about the trace as itself a piece of representation that we can then build higher order functions over. For now, what we do is we treat them, there's seeks of maps that tend to have some sort of coherence. So either they're all of the same cause, they're all for the same user. You can do sessionization where you say, okay, if there hasn't been any activity in n amount of time, then I'm going to break these into chunks. So I now have a seek of seeks. So there is a seek of, oh, this was the user's transaction today. They got back online later that day and they did the following activities, and it's all traced at the lowest level. We're adding another tracing level that goes into the probe architecture, which is from the client. So the client's based on Cognitec's pedestal architecture, a little departed from it at this point. But basically, we have an explicit representation of all the state transformations and all the actions that people are taking. So it's not hard to have a back channel from the client down to the server to essentially capture all the essential state. And so just like I described on the server side, we can now click a button and say, hey, next time the user connects, turn on their tracing apparatus, and they'll start sending me dumps of that user's experience, which I can turn on and off. And we turn a certain amount of it on because we do a lot of work with researchers who want to know what users are doing. So now we can build up a representation of all the user activity per session or per time that the app turns on. And that's all, again, represented in the context of our system where we've got all the other state to work with. So we can build actually quite powerful reasoning methods over all of this information rather than having to go out to Splunk and search through text files, which I've done and hope not to do again. The other thing that we know, of course, is that in a functional system, if you've done a good job of design, many of your functions are quite useful as probe points. So rather than having a function definition and then an explicit probe point, you can simply turn on probing at the function level. This is not the cleanest way of doing it. We're monkey patching the function, basically. And we try to be smart about not doing multiple monkey patching and being sensitive to that var being redefined during development. So I won't claim that that is 100% solid, so currently use at your own risk. But it's another good area to discuss. And what it does is it gives us the arguments, tells us whether it was at the entry or the exit point of the function. So one of the things I find sometimes when we haven't done perhaps as fantastic a job of testing the whole system as we'd like, some data will come in, triggers a condition we hadn't accounted for, and boom, we don't get an exit function. So we turn on tracing, we see it go in, we say, here was the input that screwed the function. That function's pure, so now it's easy to go back to our testing system, reproduce that state. And then this is the exit, so we get to see the return values to the extent that those things can be serialized. But one of the things you can do in your transformation function is you can walk the state model and turn everything that might be some structure that can't be easily serialized, and you can turn it into some form that you can then reify later. We can also capture probe points over state. So we can add watchers to state variables that are baked into the language and get the state transitions that are coming out of those as well and throw that into the same infrastructure. And there's administrative capacities, and we expose some functions right now for doing function composition so we can do these transformations. And I moved at a much faster pace than I thought, so we can actually have a nice discussion. So the general thing that I hope you take away from this is that we stop thinking when we design our systems about all the other stuff that happens. It's not the function we're here to perform. And think of that as first-class design goals for the system. How do we design for all of the stuff that comes downstream of having a functional spec and writing a piece of code so that we can actually be more effective over the lifetime of our program rather than just effective at meeting the current testing goals? And I'm not against logs. I think logs, for a whole variety of reasons, are still useful. In our case, we just use them for operations. So is the database up? What's going on with the primitive systems, not what's going on with our application logic, because we don't want to throw away all of that context. So with that, I'll take questions.